We've seen how neural networks learn patterns, but for tasks like translation, how do models capture crucial long-range dependencies efficiently?
Traditionally, dominant sequence transduction models relied on recurrence or convolutions. These methods had inherent limitations, especially with parallel processing.
In 2017, a paper dared to propose a new simple network architecture, the transformer. It claimed to solve many sequence processing challenges.
A simple architecture, yet it revolutionized NLP? What made it so fundamentally different from what came before?
The core innovation is profound. It's based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. This was a huge architectural departure.
So, no more RNNs or CNNs for sequence context? Just attention? What is an attention mechanism if it replaces everything?
Exactly. By using attention, the transformer became more parallelizable and requiring significantly less time to train. This changed the scale of models we could build.
Processing all parts of a sentence at once, rather than word by word, that would be a massive speed up for training large data sets.
Yes, speed was crucial, but it also proved superior in quality, achieving new state-of-the-art results on challenging language tasks.
Faster and better? Usually there's a trade-off. How can a simpler, more parallel architecture produce higher quality results?
On the WMT 2014 English to German task, the transformer achieves 28.4 BLEU, improving over existing best results by 2 points in much less time.
A 2-point BLEU improvement isn't trivial. It signals that this wasn't just a theoretical win, but a practical breakthrough for machine translation.
And it wasn't just for translation. The paper showed it generalizes well to other tasks by applying it successfully to English constituency parsing. It hinted at its foundational power.
So, attention isn't a niche trick. It's a general mechanism for understanding relationships and structure within any sequence.
A common pitfall is thinking attention means picking just one thing. Here, it's about dynamically weighting all input parts relative to each other, not selecting a single focus.
So, not a spotlight, but more like a sophisticated dimmer switch for every word, adjusting its contribution to the overall meaning?
Exactly. Now that we understand the transformer's premise, let's build the intuition for what this attention truly means and how it functions inside the model.
How does this all-you-need attention system actually process a sentence, say, for translation?
If we pop open a transformer, you primarily see an encoding component, a decoding component, and connections between them. This structure is familiar for sequence-to-sequence tasks.
So it still has that overall encoder-decoder shape, but the internal workings are where the magic and the attention happens?
Correct. The transformer's encoding component is a stack of encoders. Each one takes a sequence and refines its representations, building up understanding layer by layer.
A stack makes sense. It allows for hierarchical processing, creating progressively more abstract meanings as information passes through.
Each encoder has two crucial sublayers. First, a self-attention layer, a layer that helps the encoder look at other words in the input sentence as it encodes a specific word.
Look at other words? So if I'm encoding bank, it can dynamically reference river or money to clarify its meaning?
Precisely. After self-attention provides context, the output goes to a feed-forward neural network. This processes each word's context-rich representation independently.
So self-attention gathers the relationships, and then the feed-forward network processes that contextualized information for each individual word. Self-attention still feels like a bit of a black box. The author here says, don't be fooled by me throwing around the word self-attention. What makes it self?
It's self because it attends to other parts within its own input sequence, not an external sequence. It computes relationships among the words in the same sentence.
Consider, the animal didn't cross the street because it was too tired. A human knows what it means. The model faces this challenge. What does it in this sentence refer to?
That's a classic NLP ambiguity. An RNN might struggle if animal is too far away to effectively retain its context.
With self-attention, as the model processes it can dynamically weigh animal much more heavily. It allows it to associate it with animal.
So the model effectively asks which other words in this very sentence are most relevant to it, and animal provides the strongest link.
Think of it as a more flexible context builder than an RNN's hidden state. Self-attention is the method the transformer uses to bake the understanding of other relevant words directly into the current word.
So the RNN analogy of building context helps, but self-attention is linking directly, not sequentially remembering. It computes relationships. It doesn't just pass a state.
Exactly. It's computing these links directly and in parallel. Now that we have the high-level intuition, let's zoom in on how self-attention quantifies this linking or relevance.
I'm ready to see the actual mechanics behind this baking of understanding. How does it calculate that animal is more important to it than street?
We're now going to dive into how to calculate self-attention using vectors, which leads us to the critical query key value concept.
So we're moving from what it does to the precise how it does it, step by step using actual vector operations.
The first step is to create 3 vectors from each of the encoder's input vectors. For every word, we generate a query, Q, a key, K, and a value, V, vector.
So each word's original representation gets transformed into 3 distinct vectors, each capturing a different aspect or role for attention.
These Q, K, and V vectors are not arbitrary. They're created by multiplying the embedding by 3 matrices that we trained during the training process. These matrices learn the best transformations.
So the model learns what makes a good query or a useful key for determining relevance. That's a crucial learned component of the system.
The paper itself asks, what are the query, key, and value vectors? Think of query as what you're searching for, key as a label for content, and value as the content itself.
So if it is the query, it's asking, who am I? And the keys of animal and street offer themselves as potential answers, each with a value.
This analogy helps, but it's not a discrete database lookup. It's a continuous, fuzzy matching. All keys are compared to the query, and all values contribute, just with different weights.
So it's more like a weighted blend than a single best match. Every word gets a vote on how it is understood, but some votes are much stronger.
The next step is to quantify this relevance. The score is calculated by taking the dot product of the query vector with the key vector of every other word.
So a high dot product between it, query, and animal, key, means they're semantically similar or strongly related in the context.
To create stable gradients and probability-like weights, we first divide the scores by 8, then pass the result through a softmax operation. Softmax normalizes them to sum to 1.
So after these steps, each word gets a precise numerical weight. telling us exactly how much attention the current word should pay to every other word.
Finally, we multiply each value vector by the softmax score and sum up the weighted value vectors. This weighted sum becomes the new context-rich representation for the word.
So if animal had a high softmax score for it, then animal's value vector contributes heavily to its new blended representation.
Precisely. This produces the output of the self-attention layer at this position. This vector is now deeply enriched with information from all other relevant words in the input.
And this process happens in parallel for every word, generating context-rich representations for the entire sentence simultaneously. That's the parallelizable part.
This single self-attention mechanism is foundational. The full transformer uses multi-head attention, running this process several times in parallel, but this core idea is key.
So the full model just repeats this QKV blending multiple times, essentially looking for different kinds of relationships. Now I understand the core of attention is all you need.
The transformer's parallel attention for deep context understanding opened new doors for large language models. One of the earliest and most impactful was BERT.
So the foundational attention is all you need idea directly led to models like BERT that truly transformed natural language processing.
The paper introduces BERT, which stands for Bidirectional Encoder Representations from Transformers. The name tells you it's built directly upon the transformer's powerful encoder.
Bidirectional seems like a key word. It implies looking both ways, which was a huge challenge for previous sequential models like RNNs.
Its core was to pre-train deep bidirectional representations from unlabeled text by jointly conditioning on both left and right context in all layers. This was a significant advance.
This sounds like it perfectly leverages self-attention, allowing it to link any word to any other word in the sentence, regardless of position.
This pre-training allowed BERT to be fine-tuned with just one additional output layer to create state-of-the-art models for many tasks. This drastically reduced new application development.
So instead of building a unique model for each NLP task, you add a small adapter to BERT and it's ready to go. That's incredibly efficient.
And this approach wasn't just efficient, it was incredibly powerful. BERT obtained new state-of-the-art results on 11 natural language processing tasks, validating the transformer's design.
That's a huge claim. It shows the transformer architecture, especially with bidirectional context from pre-training, is a truly general-purpose language engine.
For example, on the challenging SQAD V1.1 question answering task, BERT pushed the test F1 to 93.2, a significant jump over prior models. This demonstrated deep comprehension.
So, BERT could not only understand the meaning of words, but also their relationships well enough to answer complex questions about a passage.
BERT exemplifies how the transformer's parallel attention allowed for scaling. Instead of learning patterns sequentially, it learned global relationships from vast amounts of text simultaneously.
It seems like "Attention is all you need" wasn't just a bold paper title. It was a blueprint for a new era of language understanding models.
So, when should you reach for this pattern? Whenever you need a model to capture long-range dependencies, deep context, and efficiently pre-train on vast text for diverse tasks, the transformer is your starting point.
It's the go-to architecture for building flexible, powerful language models, adaptable to almost anything.
I'm Maya. Thank you for thinking this through with us.
This episode really clarified how one bold architectural choice fundamentally changed an entire field.
I'm Arjun. Another idea in 3 hours. Take care of your mind.